Today, we are dropping straight into what I think is one of the grandest scientific mysteries of our entire lifetime. You see, over the past couple of decades, humanity has pulled off something truly incredible. We've actually discovered over 6,000 exoplanets. That's 6,000 alien worlds scattered across the cosmos. But there's a massive, incredibly frustrating catch to all of this. We can't actually see a single one of them. I mean, we know they're out there, for sure, but their true faces are completely hidden from us. Well, today, we're going to look at some jaw-dropping, genuinely futuristic science that is about to change that forever.
But to really grasp the mind-bending solution we're headed toward, we first have to set the stage. So let's look at Section 1, the problem of blurry planets. Because despite all of our incredibly advanced technology, these alien worlds remain stubbornly out of our visual reach.
All right, let's dive into this. On one hand, you have the famous pale blue dot. This is an image of Earth taken by Voyager 1 back in 1990 from the very edge of our solar system. Looking at it, you can tell it's a planet, right? You might even guess there's water. But contrast that with 2MEM1207b, which was captured in 2004. That was the very first direct image of an exoplanet ever taken. And honestly, it is nothing but a blurry, confusing pair of pixels. If I asked you which dot was the star and which was the planet, you'd literally just be guessing. And the really frustrating truth is that 20 years later, even with the magnificent $10 billion James Webb Space Telescope, we're still just getting slightly better fuzzy dots.
The crazy reality is, we barely ever actually see exoplanets at all. We basically just rely on indirect clues. Take the transit method, for example. We're essentially looking for shadows. When a planet passes in front of its star, the star's light dims just a tiny fraction. It's kind of like a mini solar eclipse. Then there's the radial velocity method, where we're looking for this huge gravitational tug-of-war. We measure the minuscule red or blue color shifts in a star's light as an unseen planet's gravity pulls it back and forth. So we only know these planets exist because of math, shadows, and gravitational tugs. We are not seeing their mountains or their oceans or their actual surfaces. So you might be wondering, why is this happening? Why can't we just build a bigger telescope and zoom in? Well, that brings us to Section 2. Why can't we see clearly? Let's dive right into the agonizing physical roadblocks standing between us and high-resolution images of alien continents.
The first major roadblock, it really just comes down to simple optics. To gather enough photons, those little particles of light, from a tiny, super distant planet to make a sharp image, the mirror on our space telescope would need to be massively scaled up. For context, James Webb's mirror is 6.5 meters across. To actually see an exoplanet clearly, we need a telescope mirror that is 100 kilometers across. That is practically impossible to build in space. But, let's pretend we had a completely unlimited budget and magically built a 100-kilometer mirror. We would immediately hit limit number 2, which honestly ruins the whole thing.
Okay, picture this. Imagine standing in the pitch black, trying to clearly photograph a tiny, faint firefly. Easy enough, right? But now imagine that firefly is fluttering right in front of a massive, blinding stadium floodlight. That is exactly what trying to photograph an exoplanet is like. A host star is literally billions of times brighter than its orbiting planet. We try to use tools called coronagraphs inside our telescopes to block out the star's light. But over these mind-boggling cosmic distances, the glare is just way too intense. The floodlight completely drowns out the firefly. So, does that mean we're just doomed to never see these worlds? Not quite. Let's shift the energy up a bit for Section 3, Einstein's unique idea. To find our ultimate solution, we actually have to travel back in time to a century-old loophole. And this brilliantly illustrates the core of that loophole, space-time curvature. Back in 1915, Albert Einstein published his general theory of relativity. He proposed that space and time are basically like a giant fabric. If you drop an incredibly massive object onto it, like a star, it warps that fabric. It creates a dip, much like dropping a heavy bowling ball onto a trampoline. And here is the crazy part. This curve is so strong that it literally bends passing light. Photons traveling through space get caught in this curve and are physically forced to change their path. Let's trace how this idea actually evolved, because it's pretty wild. In 1936, an engineer named Rudi Mandl pestered Einstein with this fascinating thought. If a massive object bends light, couldn't it act like a giant magnifying glass? The bent light rays could converge at a focal point, essentially magnifying whatever is behind that massive object. Einstein actually published a short note on Mandl's idea, but he kind of dismissed it. He stated that achieving the perfect alignment of planets and stars in our completely chaotic universe was so incredibly unlikely that humans would just never observe it. Well, actually, scratch that. Einstein was totally wrong on this one. Fast forward to 1988, and scientists using a radio telescope captured exactly that. They saw a foreground galaxy bending the light of a distant quasar behind it into a perfect circle of light. We call this phenomenon an Einstein ring.
Which brings us right up to the present day, and Section 4. The Sun will become a giant lens. Get ready, because the reality of NASA's futuristic master plan is absolutely mind-blowing.
Just let this question sink in for a second. What if we use our very own Sun as a 90-kilometer telescope mirror? This is the core of NASA's proposed Solar Gravitational Lens, or SGL mission. Remember earlier how we said we needed an impossible 100-kilometer mirror to see an exoplanet? Well, we don't actually need to build one. Our Sun is massive enough to bend space-time for us. If we can just position a telescope perfectly, we can let the Sun's gravity gather all those incredibly faint photons from a distant exoplanet, bend them around itself, and blast a highly magnified image straight to us.
Now, what's really interesting about this is how the process actually works, because it's not like taking a normal photograph. Step 1 is aligning our telescope, the Sun, and the target exoplanet in a perfectly straight line. When we do that, we don't get a neat photo. We get Step 2, a highly distorted Einstein ring, which is essentially just a smeared-out slice of the planet's light. It's like one single piece of a giant jigsaw puzzle. Step 3 involves slightly moving our telescope to capture different distorted rings that represent different slices of the planet. And finally, in Step 4, advanced AI algorithms will process all these distorted rings, untangle the bent light, and stitch those puzzle pieces together into a perfect, flawless map of the alien world.
So, the absolutely crucial point here is this number, 1.3, because once that AI stitches the light back together, the final map will have a jaw-dropping resolution of roughly 1.3 kilometers per pixel. That is literally insane. With that level of clarity, we aren't just looking at a blurry dot anymore. We will literally be able to see alien continents, oceans, mountain ranges, and, if they exist, city lights and massive artificial structures on planets light years away from Earth.
Now, of course, an idea this unbelievably grand doesn't come without an extreme logistical nightmare. This is Section 5, Space's Longest Journey, and executing this is going to push humanity's engineering limits to the absolute brink.
The biggest hurdle we face comes down to this number, 550. To capture that perfectly bent light, our telescope has to sit at the exact focal point of the Sun's gravitational lens. And math dictates that this focal point sits at a staggering distance of 550 astronomical units away from the Sun. For some context here, Voyager 1, which has been screaming through space for nearly 50 years, is currently only about 173 astronomical units away. If we use standard chemical rockets, it would take our telescope 140 years just to reach the starting line of this mission. That makes it completely useless for anyone alive today, right?
So NASA literally had to rethink space travel, resulting in this brilliant execution plan. First, instead of sending one massive heavy telescope, they're going to divide the mission into 6 smaller submodules. Next, and this is wild, they won't shoot them out into deep space, they will launch them directly toward the Sun. As they graze our star, these modules will deploy massive ultralight reflective solar sails. The Sun fires out trillions of photons every single second, and while photons don't have mass, they do have momentum. These solar sails will literally catch the sunlight, using the momentum of the Sun's photons to perform a violent, incredibly high-speed gravitational slingshot maneuver. By riding these photon sails and essentially using the Sun as the ultimate engine, the modules will accelerate to an astounding 25 to 30 astronomical units per year. That drastically slashes our travel time from an impossible 140 years down to a very manageable 20 to 22 years.
We are suddenly looking at a highly realistic roadmap to seeing alien worlds. Let's transition to Section 6, a clear picture of the future to look at the next steps and the ultimate vision for this incredible technology.
Because let's face it, space is dangerous, and a 20-year journey is super risky. Scientists aren't putting all their hopes into a single launch. Instead, they plan a continuous deployment network. They're going to launch a new, small module every few months. This does 3 really important things. First, it builds redundancy. If one module burns up near the Sun or its instruments just fail, there's another one right behind it. Second, it allows us to continuously update the AI and sensory technology on the newer modules as our tech evolves back here on Earth. And third, having multiple telescopes swarming the focal point means we can capture way more light, much faster, generating those ultra-high-definition images of the exoplanet.
All right, now for the elephant in the room, the price tag. Building this fleet of solar sailing modules is estimated to cost around $40 billion.
Now, I know that sounds like a massive number. It would make it the most expensive telescope in human history. But context is everything here. Adjusted for inflation, the Apollo missions to the moon cost roughly $39 billion. The current U.S. defense budget sits at $1.4 trillion. When you really put it into perspective, $40 billion to physically see the surfaces of alien worlds is a completely achievable investment for humanity.
Let's move on and see how this all builds into a concrete timeline. The underlying concepts here aren't just theoretical anymore. The initial demo phases for the solar sails and the AI algorithms actually wrapped up successfully in 2023. Based on current projections, we could see the first SGL mission launch around 2035. Factor in that 20-year travel time, and we are looking at the year 2055 when the first ultra-clear images of an exoplanet actually arrive back on Earth. Think about that. Many of us are actually going to be alive to see the first alien mountains, rivers, and continents.
And that leads us to one final, incredibly provocative thought. Because this massive network of deep space telescopes, it isn't just about taking pretty pictures. By establishing this continuous line of high-tech modules out to 550 AU, scientists are effectively laying the fiber optic groundwork for deep space communication. We aren't just building a telescope. We are literally building the first nodes of a multi-galaxy internet. The Solar Gravitational Lens will change our relationship with the cosmos forever. So the only question left is, what are we going to see when that very first image finally loads?